So here we are on page 42, and they start talking about what is calculus. So calculus is the mathematics of change, velocities, and accelerations. We will talk a lot this year about rate of change. And then quite often that rate of change represents a velocity. And then the rate of change of the velocity is what's called the acceleration. Okay? You're familiar with rate of change. When you find the slope of a line, you're finding the rate of change that that line represents. You know, like if it's, well, didn't mean to do that, but if it's like this right here, okay, if that's the graph of rate and time or whatever, you're familiar with that. But see, we're not going to find slopes of lines. We're going to find slopes of curves. All right, things that don't travel in a linear fashion. Okay, because the world's not linear. We think it is, and we use lines to model things, but for the most part, the world's not really linear. Okay, so we're going to talk about rates of change, velocities, acceleration. Calculus is also the mathematics of tangent lines. Remember what a tangent line is? A tangent line intersects a graph in one point only. Okay, and we even kind of fudge that a little bit. And sometimes if we have certain kinds of graphs, we can have lines that are tangent in an area. But due to the way the graph looks, it may actually hit it again somewhere else, but it's so far away it doesn't come into play. All right? Slopes, areas, but instead of just finding like the area of polygons or the areas of circles, we'll find the areas of irregularly shaped things and the areas under curves. Okay? And the areas between curves. Volumes, but not just volumes of prisms and pyramids and cylinders, but volumes of irregularly shaped things. Okay? And one of our favorite ones is volumes of solids of revolution. Like a baseball bat is a solid of revolution. You can put it on a lathe, well, that's where they make the baseball bat. And those are actually very easy to find the volumes of. But we'll find volumes of irregularly shaped things as well. And arc lengths, centroids, and curvatures are a little more advanced than what we're going to be doing. And a variety of other concepts that have enabled scientists, engineers, and economists to model real-life situations. We always tend to think of calculus as being for engineers, and it is, but sometimes it's a little surprising to me to find out economists use it as well when they try to figure out things, and obviously other scientists will. Okay, so look at the differences here they have set up in the chart on page 43. All right. Before you knew about calculus, you could find the value of a function at a certain x-coordinate. With differential calculus, there's two kinds of calculus, differential and integral. We'll do both. Okay. With differential calculus, we'll find the limit of a function as x approaches a certain thing. Look at the difference in the graphs here. The one on the left is just a regular graph, all filled in, but look at on the right. Look what's happening right there. That point's not actually on the graph. If we took our calculator and try, if our function was x cubed minus 7x plus 2 or whatever, and we tried to stick in that x coordinate, we would get undefined because that function does not actually exist at that x coordinate. But with calculus, we can figure out what that number ought to be if it were filled in by finding what's called a limit. We'll do a lot of limits. Okay? We can find the slope of a line already. With calculus, we'll find the slope of a curve. Here's the cool thing about the slope of a curve. At this point and at this point, do you expect the curve to have the same slope at both those points? It doesn't, because it's not increasing at the same rate at both those places, is it? Over here, the function's actually decreasing. That ought to be a negative slope, shouldn't it? And it is. And we'll learn how to find those. All right? We can find an equation of a secant line. If a tangent line only intersects once, a secant line intersects more than once. Okay? We can find the equation of a secant line because it hits the curve twice. We can figure out what those points are, and if we know 2 points, we can figure out the equation of a line. We're going to find out how to make an equation of a tangent line. With a tangent line, we only know 1 point, but we're still going to be able to figure out the equation because we're going to be able to figure out the slope of that tangent line, okay? Because the slope of that tangent line that we're talking about here and the slope of the curve that we're talking about here turns out they're the same thing, okay? So if we learn how to find the slope of the tangent line, we have also found the slope of the curve. And if we learn how to find the slope of the curve, we've also found the slope of the tangent line. So that works nicely. Right now, without calculus, you can find the average rate of change of a moving object, the average. You know, if you start at a certain time and you drive 60 miles and it took you exactly 1 hour, you went 60 miles per hour, but what, as an average. But did you go 60 miles per hour the whole time? No, because you started at 0, and if you went 60 miles an hour, you must have gone faster than 60 at some point. With calculus, we can find the instantaneous rate of change at any moment. We'll be able to say, all right, at time 0, the car had 0 velocity. At time 30, the car had a velocity of 70. At time 40, the car had a velocity of 56. We'll be able to find all that, okay? Now, integral calculus. All that we talked about so far is differential calculus, involving what's called a derivative that we'll learn. Integral calculus involves integrals that we'll learn. Right now, you can find the area of a rectangle. With calculus, you can find the area under this curve. See, that doesn't make a polynomial or a polygon of any type, does it? We can even throw in another curve and then find the area between those two curves. Or we could take several different graphs, graph a bunch of lines and a semicircle, do that, and we could find the area of all this stuff made up of all those different graphs. We'll be able to do all that, okay? It won't even be that difficult. Right now, you can find the surface area of a cylinder. Eventually, we'll be able to find the surface area of a solid revolution. That's actually Calculus 2. That's second semester, okay? Right now, you can find the volume of a prism. We'll be able to find a volume of an irregularly shaped thing like that, all right? And to be honest, those are kind of tough. That requires a lot of thought. But we'll get good at those too. So, what I hope you can see from all this is we're going from things that are relatively easy to visualize to things that are more difficult to visualize. You can visualize a prism, a box, without any trouble, right? You don't have to see a drawing of it. But can you visualize a solid form by the graph of y equals x squared minus 3, the graph of x equals 0 and y equals 0? No. But that's where we're aiming, okay? All right. Now, there's 2 huge problems in calculus that, amazingly enough, tie together. And for a long time, mathematicians didn't realize they tied together. That was the big breakthrough that Newton and a guy named Leibniz came up with that formed what we all call calculus now, okay? They figured out that these 2 problems were related, whereas it took a long time. It took, well, geniuses to put that together. When I actually put it together for you with the fundamental theorem of calculus, it will be a little bit of a letdown because it'll be like, oh, I see that. Well, of course you see that because, you know, we've been leading you to that. Up until then, nobody knew they led together, okay? So it's a tangent line problem. So take a second to read on page 45 the couple of paragraphs there before they start getting into the mathy stuff about the tangent line problem. All right, look at what I just highlighted. Read that again, what I just highlighted. Just that little phrase or part of a sentence. Do you see why that's true? If we're looking for the equation of the tangent line at this point right here, we already know what the coordinates of P are. We know that, okay? So if I want the equation of a line that goes to that point, isn't one way, in fact, the simplest way to know what the slope of the line is supposed to be? Because if you know the coordinates of a point and the slope of the line, you can use remember the old point-slope form? And you've got an equation of the line. So we kind of change the question, simplify a little bit. The question is not any longer what's the equation of that tangent line, it's what's the slope of that tangent line. Because if I can get that, I can go back to what I learned in Algebra 1 and do the rest of it. So now it's what's the slope of that line. Okay? Now, let me help you see how to figure out the slope of that line. All right, I know that's not real big, but that's as big as I can get it. All right, so that's what we're faced with. We have point P right here, the tangent line to that graph. So it touches the graph once. Through that point is that blue one I just drew in. We need to know its slope. Now, the problem is we only know one point that's on the line, so we can't use the slope formula. But look here. Here's a secant line. See point Q way up here? If I know the coordinates of Q, I can find the slope of line PQ, can't I? And if I move Q down here, the slope of that line is a little bit closer to being the slope of the blue line, isn't it? Then I move Q down here. Isn't the slope of that line even closer to the slope of the blue line? So here's what's going on here. As you move Q closer to P, the slope of the secant line begins to approximate the slope of the tangent line. Okay? And in fact, if I keep moving Q closer and closer and closer, eventually I can get it so close that I'm unable to draw it so that they look different from each other. Now, that's the idea of a limit. Okay? As I move Q closer to P, the limit of the slope of that line is whatever the slope of the tangent line is. In other words, the slope of the secant line keeps getting closer to it. The slope of the secant line never actually equals the slope of the tangent line, because if it did, then point Q would literally be on top of point P, and we wouldn't have a secant line anymore. Okay? But that's what the idea of a limit is, a boundary. All right? If I'm going to stand here and the function that I'm following says that every second the distance between me and the door is cut in half. So I start here, in 1 second I cover half that distance. The next second I cover half the distance again, half the distance again. The limit of my motion is the door. Do I ever get to the door? Nope. But the limit is the door. Just like the limit of the slope of that secant line is the slope of the tangent line. Does the secant line ever actually become the tangent line? No. But we can measure it, though. Just like if I keep getting closer and closer to the door, we can approximate the distance between me and the door as 0 eventually, can't we? The approximation of it. Will the distance ever actually equal 0? No. But the limit will equal 0. See what I'm saying? So that's what we're going to be able to do. And it looks all complicated, so we can look back there on page 45, and we can see the formula here. All right? That's just y2 minus y1. F of something is just a y coordinate, isn't it? Right? So that's just y2 minus y1. That's your first x, or that's your first x coordinate. The other x, delta x minus that's your second one. It's just the slope formula. I don't want to get into the details right now. Okay? So we're finding the limit of using a slope formula, and we'll get good at this. Trust me. Okay? Now, our other big problem is the area problem. Mathematicians wanted to be able to find the area under a curve. Now, we say area under a curve, but we got to be careful. It has to have boundaries. All right? Usually, we can change our boundaries, but the default setting is that the x-axis is a boundary, and then two vertical lines are the boundaries, and then the curve is the other boundary. So y equals f of x is the last boundary. Now, that's not a polygon, it's not a circle, it's not part of a circle, it's not part of a polygon. It's an irregularly shaped object, and we want to know what its area is. Well, we can approximate it. All right? Here's one way I could approximate it. I could pretend that it was a rectangle and find the area of the rectangle. And that would give me an approximation. Not a very good approximation of that area. And then I could say, okay, I'll make then a rectangle that's too small, using this space right here. And that's too small, but I can find the area of that. So the area of the pink region somewhere between the area of the rectangle that's too big and the area of the rectangle that's too small, right? But there's a lot of space in between, so I don't exactly where. I can do better. I can do better. Because I can do this. I say, okay, I'll draw a rectangle there. I can find that area. And a rectangle there and find that area. And a rectangle there and find that area. Get the idea? If I fill the space up with rectangles, finding the area of a rectangle is easy. Then can't I just add up those areas? And I get a pretty good approximation. If I want a better approximation, what do I need to do? If I'm sticking with rectangles, because trapezoids work really well too. Do what? Okay, I could put some above and some below and try to compensate that way. What else could I do? That's a good idea. Yeah, put smaller rectangles, which means I need more of them. Right? More and skinnier rectangles makes a better approximation. Like this. So there we start with 4 rectangles. Then they put, how many is there now? 5. Whatever. The more rectangles you put, if you find those areas of the rectangles and add them up, don't you get a better approximation of the area under the curve? Yeah. And again, that's the idea of a limit. By putting more rectangles, by putting more rectangles and adding them up, will it ever be exactly the same shape as the curve? Nope. But we'll be able to figure out what it's heading towards. All right? Like if the first time we find the area we get those rectangles, add the areas up, and we get 49.5. We put more, we get 49.6. Put more, we get 49.9. Then 49.99. 49.99999. 50 is the actual answer. Question?
You get a better approximation of like the areas where rectangles don't fill the curve. Take that as
Yes. That's a good idea. Like right here, oh, come on, let me write. Well, it's not letting me write, but see where the cursor's blinking there? Doesn't that look like a triangle? So we could go back and find the area of that triangle and add that in, right? And up here, it looks like a triangle. In fact, if I just did, well, I'm going to have to go back to this. It'd be kind of like doing this, wouldn't it? That's a trapezoid. Now, trapezoids work better than rectangles. You know what the problem is, though? They're a lot more difficult to work with. They're not impossible to work. Working with 4 or 5 of them, all right, 1/2 times the height times the sum of the bases. All right, what if we put 50 of them in there? Right? Nobody wants to do that. So, and in fact, we'll have a whole section called the trapezoidal rule, where we do it with trapezoids. So, good thinking. All right. Drum roll, please. There's your assignment.